All right, let's dive into one of the absolute weirdest, most mind-bending ideas in all of physics. It's this. Everything in the universe, and I mean everything, from a tiny little electron all the way up to you, isn't just a particle. It's also a wave. So let me ask you straight up. Are you a particle or are you a wave? And the answer, believe it or not, according to quantum mechanics, is yes, you are both. Okay, so how on earth is that even possible? Let's get into it. To really get our heads around why you have a wave nature, we've got to start with light. You know, for centuries, physicists were in this huge debate. Is light a stream of tiny particles, kind of like little bullets? Or is it a wave spreading out through space? Well, the answer turned out to be way more complicated than anyone saw coming. I mean, think about it. In our normal world, these two things are complete opposites. A particle, like a billiard ball, is right here. It has a specific spot, and you can't have two of them in the same place at the same time. But a wave? That's a disturbance, something that's spread out. Two waves can just pass right through each other, no problem. They seem like they couldn't be more different. For a long, long time, the evidence for light being a wave was just overwhelming. I'm talking about things like interference, where light waves can add up or even cancel each other out, and diffraction, where they bend around corners. You just can't explain that stuff if light is only a bunch of particles. The case pretty much seemed closed. But then, things got weird. New experiments started popping up that just didn't fit the wave picture. Take the photoelectric effect. That's where light hits a piece of metal and knocks electrons off. Well, it turns out that only makes sense if light's energy comes in these little discrete packets, particles. We call them photons now. And suddenly, physicists had solid proof for two ideas that completely contradicted each other. So this led to the wild conclusion we now call wave-particle duality. Basically, light has two different faces. Sometimes it acts like a wave, other times it acts like a particle. And the crazy part? Which face it decides to show you depends entirely on how you try to measure it. This whole thing kind of settled the identity crisis for light, but wow, it was really just the beginning. So this strange, two-faced nature of light really set the stage for an even more radical, even crazier idea. And that's where our main character comes in, a young French physicist named Louis de Broglie. He looked at this whole mess and he didn't see a paradox. He saw symmetry, a beautiful, universal symmetry. So in 1924, for his PhD thesis of all things, de Broglie proposed something incredibly bold. He said, you know what? This dual nature, it's not just a special quirk of light. He argued it was a fundamental principle of the entire universe. He posed this simple but incredibly powerful question. His logic was just so elegant. He said, look, if something we all thought was a wave, light, can turn around and act like a particle, well, couldn't the reverse be true too? Could the things we think of as solid particles, electrons, protons, you, me, everything, also act like waves? And here's the best part. He didn't just ask the question, he gave us the math. The de Broglie wavelength equation is so simple, but it is so profound. It says that any object's wavelength, that's lambda, is equal to Planck's constant, h, just divided by its momentum, p. And just like that, with one little equation, every single moving particle in the universe was given a wavelength. Okay, so an idea this revolutionary? Well, it needed proof. I mean, it's one thing to write down a beautiful equation on a piece of paper. It's a whole other thing to actually prove that an electron, the very definition of a tiny little particle, can actually behave like a wave out in the real world. And that proof? It came just 3 years later, in 1927. It came from an experiment by two American physicists, C.J. Davison and L.H. Germer. They designed this brilliant test to see if a beam of electrons would show one of the classic calling cards of a wave, diffraction. The logic was just genius. They decided to fire a beam of electrons at a nickel crystal, which acts kind of like a tiny little diffraction grating. Now, if the electrons were just tiny bullets, they should just bounce off in all directions, totally randomly. But if they were waves, they should interfere with each other and create a very specific pattern of bright spots and dark spots at certain angles. And guess what happened? They didn't see random scattering at all. They found a clear, undeniable pattern at a very specific voltage and a very specific angle, 54 volts and 50 degrees if you're curious. Bam! They saw this huge spike in the number of electrons they were detecting. This was something you could only explain with constructive interference, where all the peaks of the electron waves were lining up perfectly and reinforcing each other. This was the smoking gun. It proved the wave nature of matter. And here is the absolute kicker. This is where it all came together. Using de Broglie's equation, the predicted wavelength for an electron at that energy was 1.67 angstroms. Now, what Davison and Germer actually measured from their pattern was 1.65 angstroms. It was a near perfect match. De Broglie's wild out there hypothesis was now a hard experimental fact. Okay, so this all leads to a really obvious question, right? If every single particle has a wave, why don't we see any of this in our day-to-day lives? Why do solid objects feel so solid? I mean, think about it. If you throw a baseball through a doorway, it doesn't spread out and create an interference pattern on the wall behind it. It just goes straight through. So what gives? Well, the answer takes us right back to de Broglie's equation. It's all right here in the numbers. Remember, wavelength is inversely proportional to momentum. An electron has a ridiculously tiny mass, which gives it a wavelength that's actually measurable, about the size of an atom. But a baseball has a huge mass in comparison. Its momentum is so large that its wavelength becomes, well, astronomically small. We're talking 10 to the power of negative 35 meters. And that's the whole secret. A wavelength of 10 to the minus 35 meters is trillions of times smaller than a single proton. It is so unimaginably, ridiculously tiny that we could never, ever hope to build an experiment that could possibly detect it. So the funny thing is, you are waving right now, but your wavelength is just way too small for anyone to ever notice. So, let's wrap this up. What does all this actually mean for how we understand reality? Well, it means that at the most fundamental level, the universe is a much stranger place than it looks. This wave nature isn't just some weird quirk. It's a core property of matter itself. Every single moving particle has a wave that sort of guides its motion. And this duality, this two-faced nature, leads directly to one of the absolute pillars of quantum mechanics, uncertainty. See, because a particle is also a spread-out wave, you can never know both its exact position and its exact momentum at the very same time. And you know, this isn't just some abstract theory for philosophers to argue about. The wave nature of electrons is what makes amazing technologies like the electron microscope possible. By treating electrons as waves, we can use them to see things that are way too small to ever be seen with waves of light. De Broglie's dream is now an essential tool that we use in modern science every single day. So this leaves us with one final, really mind-bending thought to chew on. This matter wave we've been talking about, it's really a wave of probability. It doesn't tell you where a particle is. It only tells you where it's likely to be found when you look. So if the fundamental building blocks of our entire universe aren't solid little points, but are actually just clouds of pure possibility, what does that say about the nature of reality itself?